Hello all. I'm Catherine Sanchna, a PhD scholar from IIT Madras. I am one of the TAs for this course, Mechanical Characterization of Bituminous Mixtures, Bituminous Materials, that is offered by NPTEL. Now we are into the ninth week. So this session is offered every Tuesday between 6 p.m. and 8 p.m. Where we will be discussing previous year's assignment problems. Also, some of the concepts related to that. So this video will also be recorded and posted on my YouTube channel, the link for which will be provided by the NPTEL team. And also, if you have any questions, you can post it in the discussion forum in the NPTEL website, or you can comment below the YouTube video. So without any further delay, we will begin with today's session. Okay, so this question, before we get into the questions, we will just have an overview of what lectures were covered as part of week 9. Okay, so there was one lecture on oxidative and non-oxidative aging. Okay, 3 lectures on mixing and compaction temperature. Okay, and 1 lecture on dynamic modulus of mixture. Okay, just the part 1. The second part will be covered in the next week, in week 10. Okay, so we will be going through the questions, and as and when required, I will be explaining each and every concept in detail if it is required and for that question. Okay, so this question is taken from this week's assignment problem, that is week 9's assignment problem, which comes under the questions which will not be graded. Okay, there were actually 5 questions, but I've removed 4 of them because they were all on rut wheel testing, which is yet to be covered. So I have removed that, and I will be adding that when ma'am teaches, or when we get into the week that has rut wheel testing. Okay, so I just picked one question which must be very familiar to all of you, because this is very basic, and it very basic regarding the design of bituminous layers, or designing the pavement layers. Okay, so as per IRC 37, the distress transfer function for fatigue relates the fatigue life of bituminous layers to what? So if you see, you know the layers of the pavement, right? You know that there are 2 layers of bituminous mixtures. Okay, so this will be my binder course, this will be my wearing course. Okay, and mostly this will be a DBM mixture, and this will be a BC mixture. BC mixture corresponds to bituminous concrete, and DBM mixture corresponds to dense bituminous macadam. Okay, below the bituminous layers, okay, these 2 constitute the bituminous layers. Below the bituminous layers, we have 2 layers of granular materials. Okay, one is the sub base and the other is the base. These are granular materials, and the bottommost layer is my subgrade, or the foundation soil. Okay, so the strength of the foundation soil is measured in terms of what we call it as the CBR value, right? So either you take the actual subgrade, CBR of the actual subgrade, or if it is not of the required CBR value, then you will compact it and you will take the CBR value of the compacted subgrade. Okay. Now on top of the subgrade, we have something called as the granular layers. Okay, and these layers constitute the base and the subbase courses. So the properties of this layer, we measure it in terms of what is called as the resilient modulus of the granular layers. And on top of that, we have the bituminous layers. Okay, the property of which is measured in terms of many modulus values, some of which are dynamic modulus value and resilient modulus value. The dynamic modulus value is what is covered in this week. Okay, so ma'am also was saying that you need a material property for the bituminous mixture so that you can design the pavement, right? And one such material property is dynamic modulus, because it tries to take into consideration it not so it takes into consideration the the parameters which influence the properties of the bituminous mixtures, which will be temperature, frequency, and so on, right? So now when you're designing, you know that so this is just a basic overview of the pavement layers and the material properties required for each layer. Now you know that a bituminous pavement has uh, two major distresses. Okay, one is fatigue cracking. We already saw this in the previous lectures, and the other is rutting. So we saw this in terms of binder, right? Superpave grading, PG grading we saw. So fatigue cracking, you know that it is the alligator or map cracking that is observed on the top layer of the pavement, and rutting is the permanent deformation along the wheel path. Okay, there are two ways for which two contributions for this rutting. One is the mix itself is not properly designed. That is when you consider the bituminous properties, the properties of the bitumen to take care of rutting. Okay, so the mix has to be properly designed. If not, the mix itself will undergo rutting. Only the top layer, okay, will undergo rutting like this. Okay, so this is rutting. This is one type of rutting which occurs when the mix is not properly designed. That is why you consider the binder to have a few properties such as G star by sine delta value to take care of rutting. And there is one more rutting, okay, which is contributed by the subgrade. So if your subgrade is not compacted properly, I said that the subgrade has to have a certain CBR value, right? If it is not compacted properly, or if its CBR value is less, then your subgrade is going to deform like this, a big bowel shaped deformation. Okay, and because of this, the top layers will also get deformed in the same way. So if you see, the topmost layer will get deformed something like this. Okay, so in order to prevent this rutting, or in order to take care of this rutting, they said that you have to limit the strains, vertical strains on the top of the subgrade, because it is assumed that the subgrade is the contributing factor for this rutting, while considering that the bituminous mixture does not contribute to rutting. It is only the subgrade that contributes to rutting as per IRC 37. Then you have to limit the vertical compressive strain on the top of the subgrade. Okay, only then you will be able to limit the rutting. Okay. And you also have a distress equation which relates the rutting life of the pavement with the vertical compressive strain on the top of the subgrade. Okay. Now, in order to design for a given fatigue life, okay, fatigue is what occurs on the bituminous layer, right? And they say that this occurs because when a wheel load acts on the bituminous layer, there is a tensile strain. Okay, there is a horizontal tensile strain that occurs at the base of the bituminous layer. Okay. And this horizontal tensile strain is what is assumed to contribute to the fatigue cracking. So in order to know the fatigue life of the material, there is an equation in IRC 37 which relates the fatigue life with the vertical compressive strain on the top of the subgrade as well as the modulus of the bituminous mixture. Okay. If you know these two values, that is the vertical compressive strain on the top of the subgrade and the modulus of the bituminous mixture, okay, then you will be able to know the fatigue life of the pavement. Okay. For instance, if the tensile strain is very large, then the fatigue life of the pavement is going to be less. Okay. Um, it is a function of, I will write it like this because it is not directly proportional to the tensile strain on the top of the on the bottom of the bituminous layer, but it actually is inversely proportional to. Okay. So if the tensile strain is more, then your fatigue life will be less. Okay. So if you see here, the right option would be maximum horizontal tensile strain at the bottom of the bituminous layer. So it is not the maximum horizontal tensile strain at the top of the bituminous layer. Okay, they are not considering that. It is not the maximum compressive strain at the top of the bituminous layer. No. And it is also not the maximum compressive strain at the top of the subgrade because that corresponds to rubbing. Okay. Now moving to the next question. These questions, the following questions which we will be seeing correspond to um, previous year's assignment questions. Okay. So if you see, so we've come to mixing and compaction part. So bitumen during mixing with the aggregate in the mixing plant is expected to exhibit what? Okay. So for selecting a proper mixing and compaction temperature, okay, you select the mixing and compaction. So what is mixing and compaction temperature? It is the temperature to which the bitumen should be heated so that it can coat the aggregates, right? So why should the bitumen be heated? Because its viscosity is high at lower temperatures, and for it to have the lubricity, it has to be heated. Only then its viscosity will decrease and it will be able to evenly coat the aggregates. Now once it has coated the aggregates, so till now it acts as a lubricant, and once it has coated the aggregates, its viscosity, so its temperature will decrease and its viscosity will increase, and actually it should act as a glue. So it has to serve two purposes. First, it has to provide workability, and then it has to provide the strength also by acting as a glue. Now see, in the case of cement, okay, let us take concrete. There also the binder is your cement. And how will you get workability of the cement? You add water to it, right? And you will get the required workability, okay, plus aggregates, and you will get the required workability. So the workability is determined in terms of the cement water to cement ratio, right? Now once you've mixed the concrete, now the same cement should hydrate and provide a provide binding property to the aggregates. So it has to provide strength to the concrete, okay, as in it has to bind the aggregates, and the entire mixture is to provide strength. Okay, so it acts as a binder as well. Okay, here water is which is the major contributor to the workability, water to a major extent, and also the water to cement ratio. But here in the case of bitumen, your bitumen should provide both workability, okay, and after that it should serve as a binder. So while mixing, it should be heated so that it can provide a workable mix so that it can evenly coat the aggregates. And once the mixing and once it has been laid in the field, its viscosity will it should act as a glue, it should act as a binder. Okay, now during this process of mixing and compaction, in order to provide a uniform coating to the aggregates, its behavior should be Newtonian. So first, now that I told the answer that its behavior should be Newtonian, let us understand what a Newtonian behavior is. Okay. So how will you determine? So let us say I'm talking in terms of viscosity, right? Because at higher temperatures, the bitumen will be fluid like, and the property which can explain a fluid is viscosity. One of the properties which can explain the properties which can explain a material is which can explain a fluid material is viscosity, right? So at high temperatures it is going to be um, very less viscous, which is going it is going to act as a viscous material, and so we measure something called as viscosity. Now this viscosity, how will you measure viscosity in the laboratory? So if you see, the equation of viscosity is shear stress by shear rate. Okay, this is called as apparent viscosity. Why do I call it as apparent viscosity? Let us see why. So you should understand the equation of viscosity first. It is just shear stress divided by shear rate. Now there are Newtonian behavior is one in which your viscosity will not vary as you keep varying the shear rate. So it is more or less like measuring the modulus of a elastic material. Say I am having a steel rod and I am measuring its modulus. Okay, so E is my modulus. What is the formula for E? Young's modulus. Young's modulus is equals to stress by strain. So as long as the material response is linear, if I keep varying the strain, my modulus is not going to vary, because my stress will also vary correspondingly, such that the stress to strain ratio is maintained. That is, my modulus remains constant. Similarly, in the case of viscosity, I am telling you that there is a shear stress and there is a shear rate. Okay, so if I apply a shear rate to a material, it's going to have some shear, it's going to have some shear stress. Okay, right. Now if I keep changing this shear rate, and if my viscosity does not vary, that is, I make a plot of shear rate versus shear stress versus shear rate, it is going to have the same behavior as that of a Young's modulus. That is, its slope is going to remain constant. Okay? So even if I keep increasing the shear rate, the slope is not going to vary, or the viscosity is not going to vary. This is called as a Newtonian response. Okay, so no matter what the shear rate is, your viscosity is going to remain the same, right? Now in mixing and compaction temperature, in mixing they are targeting for a Newtonian behavior, because there are aggregates and there is your bitumen, and when you try to mix the aggregates and the bitumen, there's going to be interactions at the not interactions, there's going to be shearing, okay, at the interfaces. And if your viscosity is independent of these shear rates only, it can evenly coat the aggregates. If it is going to keep changing with as your shear rate changes, because in the entire mixture will not have the same shear rate. Since there are n number of interfaces, there are going to be n number of shear rates. Okay, so you cannot assign one specific shear rate to the material, and therefore if your viscosity is going to keep changing depending on the shear rate, then then it cannot efficiently coat the aggregates. So you target for a Newton for the material to have a Newtonian response. Only then its viscosity is independent of shear rate and it can evenly coat the aggregates. Okay, so that is why we target a Newtonian response for mixing and compaction. Mostly for mixing, okay, because it has to coat the aggregates. Now, um, now that I explained what a Newtonian behavior is, let us see what a non-Newtonian behavior is. Okay, so the equation of viscosity is still the same, or it will become a function. It will become a function of shear rate. Okay, so the equation will still be the same. Okay, but at every point of shear rate, I have to measure the shear stress and I have to find the ratio. That is why I am calling it as apparent viscosity, because it is going to keep changing with shear rate. Okay, so if I make a plot of shear stress versus shear rate, then my slope is not going to remain constant. If you see, my slope will either increase or decrease. Okay, so this here the viscosity increases or the slope increases, and here the viscosity or the slope decreases. This is called as a shear thickening behavior, and this is called as a shear thinning behavior. Okay, now there are also other materials which we will see as an when we go. There are questions on that also. So these two types of responses are called as non-Newton. The fluids which exhibit these kind of responses are called as non-Newtonian fluids. Okay, so this is what I wanted to say regarding this part. Now moving to so that is why we have not selected non-Newtonian nor shear thickening nor shear thinning, because all these correspond to non-Newtonian behavior which we are not going to target. Now the next question, the vibratory roller, pneumatic roller and the steel wheel roller are used for the compaction when the bituminous mixtures are typically in the temperature range of what? So if you see, when you compact your bituminous mixtures in the field, it has to have a certain density. Okay, that is why you are compacting it. Okay, now how will you compact it? There are so in the there are you know what are the compaction methods in the lab and what are the compaction methods in the field. In the field, you compact using rollers, and there are different kinds of rollers. Okay? One is a vibratory roller, which means your roller will vibrate at a particular frequency. The other is a pneumatic roller, which will have rubber phased tires, okay, and it will do the kneading action just like you knead the dough. Okay, and the third one is a steel wheel roller, which will provide a good finish to the compacted surface, because when you do these two, your surface is not going to have a good finish, and obviously for riding you need a proper finish, right? So that will be taken care of by the steel wheel roller. So obviously this has to happen at the last. So if you see, if if this compaction is going to happen at the last, it means my temperature would have reduced substantially, and also a high temperature is not required for steel wheel rollers. We do not want it, because your aggregates should have glued a little bit, right? Only then it can provide a good finish. So this is what is going to happen at the end. So if you see, of all the three options, this is the option that corresponds to this, right? In all the other cases, your lower temperature, your temperatures corresponding to vibratory or pneumatic rollers is said to be from 90 to 70, which is not the case. Okay, and also vibratory roller provides, okay, vibratory roller is the one which happens first, okay, and after that pneumatic roller. So from 150 to 115 degrees Celsius, then the vibratory roller is to be used. Then from 115 to 90 degrees Celsius, the pneumatic roller is to be used, and from 90 to 70 degrees Celsius, the steel wheel roller is to be used. Okay. Now moving on to the next question. The selection of appropriate mixing temperature helps in what? Okay. If you see here, they are talking about mixing temperature. So first identify which corresponds to mixing. Okay. If you see, the first option corresponds to compacting, preventing mix from flowing away from the compactor during compaction. For that you have something called as the compaction temperature. Okay. So for mixing, your temperature, usually your mixing temperature will be higher than the compaction temperature. Why? Because for mixing you have to coat the aggregates, and for compaction, though it has to have the lubricity to get compacted and have the particular density, the compaction temperature will not be as high as the mixing temperature. Okay. So though option 1 is correct corresponding to compaction, it does not correspond to the mixing temperature. It corresponds to the compaction temperature. So option 1 is not correct. Then the next option, achieving the uniform coating of bitumen over aggregates during mixing. So this corresponds to mixing temperature, correct? So in mixing, we target a coating of a film thickness of 10 microns, right? It is just an arbitrary value, or it is assumed that whatever the mixing temperature that you choose provides a uniform thickness of 10 microns, a micron coating around the aggregates, right? So a selection of appropriate mixing temperature will help you to achieve a uniform coating of bitumen of the aggregates during mixing. Now the next option, compacting the aggregate to achieve the required density. Here also this corresponds to compaction and not the mixing. So it has nothing to do with the mixing temperature, though compaction does help you to achieve the required density. For that only we use the compaction temperature and not the mixing temperature. So the answer to this is achieving the uniform coating. Moving on to the next question. In measurement of dynamic modulus as per AASHTO TP 79, which among the following statement is true? So this is one of the modulus measure for a bituminous mixture. Right? Now, how will you measure this modulus? On what sample is it measured, and what type of loading is applied, and what response is captured from the sample? So let us first understand why a dynamic modulus value is required. As I said earlier in the first question, if you have to know the response of the pavement, say I am applying a wheel load to the pavement, it will undergo deformations, right? It will show its response in terms of stress, strains, and deformations. So if I have to know this, if I have to capture the stress, strain, or deformation, then I should know the properties of the material, right? And I should also know the I should also understand the material. Say, I will not use the same property for bituminous mixture and granular mixture, granular material. Why? Because the bituminous mixture will respond in a certain way, and the granular material will respond in a certain way. For instance, my granular material will not depend on the temperature, right? It will depend on other factors such as the moisture content and so on. But a bituminous mixture, the properties will depend on the temperature. For instance, since bitumen is a is a temperature dependent material. If your temperature is high, then your the modulus of the material is going to be less. And if your temperature is low, it will behave like a more solid like, and the modulus is going to be high. And we all know that bitumen is a rate dependent material also, which means depending upon the time of loading or the frequency of loading, my response is going to vary. So the modulus of the material is going to be different, right? So if the rate of loading is very high, then your material will be solid like, and therefore the modulus will be high. If the rate of loading is less, then your material then your mixture will perform fluid like, and so its modulus will be less. So now you cannot use the same modulus that you cannot use the same test that you use for a granular material to capture the to determine the property of the bituminous mixture, right? Because the influential parameters of a bituminous mixture and a granular material are different. Now for that only we get into something called as the dynamic modulus, because here we do a kind of testing which can capture the variation of the bituminous, the modulus of the bituminous mixture with temperature and frequency. Okay, so what you do is you take a sample of a cylindrical sample, okay, a bituminous mixture. So you how do you do that? You take the aggregates, mix it with bitumen, okay, at the mixing temperature. Then you compact it using a gyratory compactor. So we did not get into the types of the compacting equipments. There are three types of compacting equipments, three equipments in the laboratory for compacting the bituminous mixture. One is a Marshall compactor, which will compact by impact, okay. It will provide impact to compact the bituminous mixture. The second one is a gyratory compactor, which will provide kind of a kneading action. So it will also induce shear to the sample in order to compact the bituminous mixture. And the other one is a shear box compactor, which is again used for compacting with the help of shear. Okay. So here in this case we use a gyratory compactor. Now this gyratory compactor, from this gyratory compacted specimen, you core out the specimen of the required diameter and height, and then so it will be 100 mm diameter and 150 mm height sample. So you core it out. Okay, before that you should short term age the mixture. Okay, so after mixing and mixing, you short term age the loose mixture, okay, in the oven for 4 hours, and then you take it and compact it in the gyratory compactor. Now once you've sliced the sample to the required dimensions, you should apply some loading on the sample to measure the deformations. Okay, so for dynamic modulus you do a stress control test. Okay, so if you are doing if you are controlling the stress, what will you measure? If you are controlling the stress, you will your response will be strain. How will you get the strain? You have to measure the deformations, and from that you can calculate the strain. Now this is unlike your bitumen, this is a big sample, right? And you assume it to be homogeneous, but it is obviously a mixture of aggregates and bitumen, right? Now its response at different points may not be the same, so you cannot simply measure the deformation. So this is the plan view, okay, the top view. So you cannot simply measure the deformation at just one point and calculate the modulus of the material. You have to have at least 3 points. So you have to have 3 points, not at least, you have to have 3 points to measure the deformations, okay, and they should be 120 degrees apart. So totally it is 360 degrees, right? So if it is 3 LVDTs, like LVDTs are what are used to measure deformation. So if there are 3 LVDTs, then they have to be equally spaced at 120 degrees apart. And what will you do? You will find out the deformation at the 3 LVDTs, find out the corresponding strain, and take the average value, okay. Why do you do this? Because your bituminous mixture, though you assume it to be homogeneous, practically it will have different deformations. It can have different deformations at different places. Most probably it will, right? Because it is a mixture. Now you have to be as correct as possible. That is why you are, instead of relying on just one point, you are going to take 3 points and take the average of it, okay. So how else? So now I told you that these LVDTs have to be placed at 3 points, right? They will not be placed, okay. So this is the top view. If you see the side view or the front view, okay, whatever it is a cylinder, so no issues. So if you see, you will not place LVDTs on the top and bottom because of the end effects, okay. Since you are applying load here, there will be end effects on the sample, so you place the LVDTs at the center, okay. So this is regarding where to place the LVDTs to measure the strain. A few questions down the lane, I will be talking about what kind of load should be applied to the dynamic to measure the dynamic modulus. Since this question talks about only the measurement of strain, I have just spoken about the LVDTs, the position, and where should be the position, and how many should be placed, okay. So let us go through these options and see which one is correct. The strain is measured for the full length of the specimen. Just now I said it will be measured at the center because of the end effects, okay. So this is not the answer. The strain is measured for a gauge length of 120 mm. So the total height is 150 mm, okay. So if the gauge length is 120, it will again be closer to the ends. So you do not measure the strain for a gauge length of 120. Gauge length is the distance for which the change in length is measured, okay. You will not take the entire length of the sample, but you will take only a small portion of the sample, okay, where you do not have these end effects. The strain is measured using 3 LVDTs placed 120 degrees apart. Yes, this is what we saw. Bituminous homogeneous, and hence the measurement at different points along the circumferences will be the same. We, in any model, okay, so if you are planning to model the bitumen, or if you are even in the design of the pavement layers, we assume the bituminous layer to be homogeneous, but obviously it is not homogeneous, okay. It is just an assumption, and so when you're making the measurement, you cannot simply just take one part, because your sample is homogeneous, inhomogeneous. So you have to measure at least at 3 points. So this also is not the option. Now moving on to the next question. While compacting the bituminous mixture in the gyratory compactor, the required shear force is applied by to the sample by controlling the water. So if you see, so how will this gyratory compactor work? It will have an axial load, okay, of 600 kilopascal. The compactor will have a angle of 1.25 degrees, okay. So it will keep moving in this angle, which will offer the shear force, okay. It will so so the number of gyrations is the number of rotations, okay, and diameter of the sample. So these are the four options. If you see, obviously the diameter of the sample has nothing to do with the shear force. The number of gyrations also has nothing to do with the shear force. The only thing that could, because they do not depend on the force, right? The only thing that could offer shear force is axial load or gyratory angle. Though gyratory angle also does not have anything to do with shear force, how it will provide the shear forces, you have a axial load and you are applying the axial load for a sample which is at an angle, right? So when you do that, some portion will be subjected to axial load, and so if you resolve the forces you will get shear forces also. So this shear force is only because of the uh, angle of the gyratory compactor. Had the sample, had the mold been exactly vertical, and if you apply a axial load, what will happen? It will just have axial deformation and axial forces will be applied on the sample, right? Because it is perfectly vertical. um, if you if you just slant the mold and you apply a vertical load, then some force will act as an axial force, and the remaining some will. So if you resolve the forces, you will get both axial and shear forces, and it is only because of this angle. So the answer to this is gyratory angle of 1.25 degrees, right? Now moving on to the next question. Mixing and compaction temperature recommended by the superpave mix design for unmodified bitumen binder is what? Okay. So if you see, as I said, you are targeting a Newtonian kind of response for the material in order to mix and compact the bituminous mixture. So from time ahead, they have been using viscosity to fix the mixing and compaction temperature. So the first thing that they did was, okay, there was, obviously there would have been an evolution of the methods to find out the mixing and compaction temperature, right? So the first method, which was developed by the Asphalt Institute, was by using a Seybold Furol viscometer, okay, where you measure the temperature, where you measure the viscosity at different temperatures and find out the temperature. So make a plot of temperature versus viscosity graph, and temperature versus viscosity graph, and you find out the temperature corresponding to a particular viscosity. So here you find out the viscosity corresponding to 85 and 140 as the mixing and compaction temperature, right? So now, after the AI Institute, Asphalt Institute, The next method which came into existence was the rotational viscometer, okay, where you measure the viscosity. So you have so what actually will happen in a rotational viscometer, you will have something called as a cup and you will have something called as a bob. Okay, so this cup will be filled with the sample, and what you will do, you will rotate the bob. The cup will be held stationary, and when you rotate the bob, a shear rate will be induced in the sample, right? And because of this shear rate, from this shear rate, so you will have, so this rpm, from this rpm you can find out the shear rate, okay? And there this spindle, in order to rotate the spindle at this particular rpm, the instrument has to provide a torque to this spindle, right? And based on what the equipment, sorry, what the sample is in between the cup and the bob, okay, if the viscosity is high, then a higher torque will be required to rotate the spindle, okay? And if the viscosity of the material is less, then obviously there's not going to be any drag here, right? There's so a lesser torque is sufficient, okay? So from this torque which is required to rotate the spindle, you can measure something, you can measure the shear stress, and from the shear stress and shear rate you can find out the viscosity. Now what they are saying is, you find out the viscosity at different temperatures. They are not mentioning anything about the shear rate. We saw earlier that viscosity depends on shear rate. So if I rotate it at 1 rpm, say 50 rpm, if my material is non-Newtonian, it is going to have a different viscosity, and if I rotate it at 60 rpm, it is going to have a different viscosity. So they have not mentioned the shear rate, but they have simply said that you just measure the viscosity at different temperatures, and then again you make a plot of viscosity versus temperature. Now for mixing temperature, you find out the viscosity corresponding to 0.17 plus or minus 2 pascal second, and for compaction temperature, you measure the temperature corresponding to 0.23 plus or minus 0.03 pascal second. So this temperature you will take it as the mixing temperature, the one which is corresponding to 0.17, and the one corresponding to 0.323 you will take it as the compaction temperature, okay? Now there are other methods which came later, okay? One easy way of doing it is asking the manufacturer, okay? Because as sir said, finding out the mixing and compaction temperature is not easy, okay? So and more complicated in the case of a polymer modified bitumen. So if it is a polymer modified bitumen, you can even ask the manufacturer as to what should be done, okay? What should be the mixing and compaction temperature. For modified bitumen, though there are many ways of finding it, okay? Yeah, these two will hold more for modified bitumen, because modified bitumen is what will exhibit Newtonian temperature, so Newtonian non-Newtonian behavior at even up to a very high temperature, say 150 degrees Celsius. So unmodified bitumen will exhibit non-Newtonian behavior only around 100 or 80 degrees Celsius, but in many cases, okay, modified bitumen is what will exhibit a non-Newtonian behavior even at a considerably high temperature. So in that case, you will go for the third method, or you will ask the manufacturer as to what you should do. In the case of unmodified bitumen, Okay, what Superpave has suggested. So the second method corresponds to what Asphalt Institute suggests, and what Superpave suggests is the first method, where you will measure viscosity using a rotational viscometer and find out the viscosity temperature corresponding to viscosities of 0.17 and 0.23 Pascal second. Okay. Now moving on to the next question. Dynamic modulus test is conducted on the bituminous mixture specimen prepared with what? So a few minutes back we were discussing about how the sample should be prepared for a dynamic modulus test, and I told you that before, so it has to be compacted using a gyratory compactor, but before you do that you have to short term age the loose mixture, and then you have to compact the short term aged sample. Okay, so if you see, the dynamic modulus test has to be conducted on a short term aged specimen. Okay, now moving on to the next question. Under sinusoidal loading, the dynamic modulus is the ratio of what? So before we get into this, let us first understand what kind of loading is applied to measure the dynamic modulus of bituminous mixture. So you have a cylindrical sample. Now we saw that it has to capture the influence of frequency and temperature. So I need to first carry out the experiment at different temperatures. Okay, and I also should carry out the experiment at different frequencies. Why? Because I have to identify the influence of the bituminous mixture on temperature, identify the influence of temperature and frequency on the modulus of the bituminous mixture. Next, I can do it in the confined state or unconfined state. So what do I mean by confined state, and why is it required? So if you see, this you are trying to replicate the bituminous mixture in the field, right? So this bituminous mixture, this cylinder will not stand alone on the bituminous pavement, right? It will be surrounded by the bituminous mixture. It's like you're taking a core from the bituminous pavement, bituminous mixture, bituminous layer of the pavement, right? Which means this is not going to be standing alone, but it will be surrounded by the entire lot of the bituminous mixture. So in that case, even when, so let us say you're providing some load to it. Okay, if it is not confined, okay, it will easily, so if I'm applying a compressive load to it, it will easily bulge, okay, and its modulus will be less. But if I provide a confinement to it, okay, some sort of confinement is provided to the sample, and this will not allow the sample to easily bulge, because it is offering a resistive force along the sides. Okay, so when you do this, when you do a confined, when you provide a confinement while testing the dynamic modulus, right, you are actually trying to replicate what is actually observed in the field, because your sample will have a confinement around it. In the also you can do testing testing in the unconfined state also. Okay. Now what kind of load should I apply? Should I apply a stress? Should I apply a strain? Should I apply compression, or should I apply tension? Okay, because I'm applying axial load, it can obviously be either compression or tension, nothing more than that, right? Okay, or should I apply a combination of compression and tension? So if you see, in order to so it has to capture the influence of frequency, right? So when does this frequency occur? My loading has to be periodical. Okay, it cannot be a time controlled time domain test. What do I mean by a time domain test? I cannot simply apply a constant compressive force to the sample. I cannot capture the influence of frequency then. Okay, so in order to capture the influence of frequency, I have to apply different cycles of loading. Sorry, not different cycles of loading, continuous cycles of loading, where frequency can be said as number of cycles per second, something like that. Okay, so now which type of loading will actually represent what is happening in the field? Certain studies have said that if I'm trying to measure the response of the material at this point, so let us consider this is my pavement and I'm trying to measure the stress or strain response at this point. There is a vehicle passing from here to here. What will happen when your vehicle is here? The strain on the material exerted by this material is going to be less. As the vehicle comes closer and closer, the strain exerted on this material exerted at this point is going to be higher, right? And it is going to be maximum at this point, and then as it moves away from this point, the strain is going to decrease, or the stress is going to decrease. Alright, so let us talk in terms of stress. The stress is going to decrease. So if I see this point, the variation is in stress when the vehicle moves from left to right is going to increase. So it is going to increase and then decrease. So that can be represented either by a triangular loading or a Haversine loading. So what is a Haversine loading? It is a sine. It is a sine wave, not a sine wave. So if it is a sine wave, it has to be like this. If it is a sine wave on the positive side, it has to be like this. But it is not a sine wave. We call it as a Haversine sine wave. A Haversine wave where it will be like this. Okay. So now when you so it can be represented either by a triangular load or a Haversine load. Now when you do this, so researchers have said that out of these types of loading, these two types of loading, a Haversine load represents close enough to what is happening in the, so close enough to what the stress experienced by a point in the field. Okay, so here also we are going to adopt Haversine loading. Okay, so it is actually a sinusoidal loading which will so here we are going to adopt Haversine loading, and this Haversine is going to be compressive in nature because applying tension on mixtures is difficult, right? So you are going to apply a compressive force in the form of Haversine loading on the bituminous mixture. So now how will you do this? So I need the response of the material at different temperatures and different frequencies, right? So what I will do is I will take a sample and I will condition the sample, okay, so that it is brought to the required temperature. Okay, I will put it in an environmental conditioning chamber, and then I will identify how much time is required for the sample to reach that particular temperature by using a dummy sample. Okay, first I will do that with a dummy sample to see how much time is required. Then I will put my original sample and then wait for wait for that time duration so that my entire sample reaches the loading temperature, okay, particular temperature. Now you have to, so you have to hold the sample at that temperature, and then you have to apply Haversine loads at different frequencies, And how will you apply these different frequencies? You should always start from the highest frequency and then go to the lowest frequency, which could be zero point 0.1 hertz or 0.01 hertz. And if you, so this is for one sample. Now if you're planning to do all the temperatures on the same sample, what you should do is you should always start from the highest, sorry, lowest temperature to highest temperature. This is for temperature and this is for frequency. Why is it like that? Why do you think you should go from highest frequency to lowest frequency or lowest temperature to highest temperature? So if you see, at higher frequency the material will behave solid like, okay? So it will not have residual strains, okay? And also in the case of lowest temperature, your material will behave solid like, and so it will not have residual strains. It will not have irrecoverable strains, okay? As much as a lower frequency or a highest temperature has. So always, so if what will happen if it has irrecoverable strains? If you do it on the same sample, then it's going to affect the subsequent values that you for the loading that you keep on applying, right? So for that case, you should first start with the frequency or temperature at which the material response strains are recoverable, okay? So if your sample, if you say that even at the lowest temperature you're observing an irrecoverable strain, so what you could do is you should change the sample, okay? Now how much load should I apply? You saw I should apply it at different frequencies, different temperatures. Now how much load should I apply? So if you see, the loading should always be applied such that the material response is linear viscoelastic, and they give you a particular set of strain, so a particular strain value. So for confined there is a particular strain value, okay, and for unconfined there is a particular strain value. So they say that if you say let us say 75 to 120 for example, if I'm loading the sample at a particular load, okay, and if I measure the strain, then if the strain is within the 75 to 120 microns, then my material response can be considered as linear viscoelastic. Now so this is kind of an iterative process, like right, because you do not know the property of the material. You do not know what could be the modulus of the material at a particular temperature and a particular frequency, right? Because the modulus will vary with temperature and it will vary with frequency. If the modulus keeps varying, then your stress required to produce this strain also varies. So what will you do? So what it actually will do is you have to give, so it actually has to do a trial run first, okay? It has to find out, so let us say I'm testing it at 25 degrees Celsius and 25 hertz, okay? So this is the first frequency that I'm going to apply to the material at this 25 degrees Celsius. So what it will do, I have to provide something called as a modulus value, say a seed modulus. We call that as a seed modulus because what the equipment will do is it knows that you require a strain of 75 to 120 or 125 micron. So using this modulus, it will find out what stress has to be applied on the sample. So it will apply that stress to the sample, okay? So it will apply 5 cycles. Now it has applied, say for example, for this strain, so for this modulus, let us say like 200 Pascal is required, 200 Pascal stress is required. So what it will do, it will apply 200 Pascal to the sample for 5 cycles. Now it will actually measure the strain which the material exhibits for this 200 Pascal. Let us say the value that we got is around 60 microns, which means my sample, so it is not in this, the strain is not, let us say it is 130 micron. Okay, so it is not within this range, right? So what it will do, it will decrease the stress. It knows that the modulus that I gave is wrong. The modulus, so from this it will compute the modulus of the material, and what it will do, it will, based on this modulus, it will reduce the stress such that the strain again falls in this range of 75 to 120. So now it has reduced the stress, and again it will apply five cycles. These are called as conditioning cycles, and after that it will apply 10 more cycles. Okay, these 10 cycles only it will take for calculations or analysis. Okay, now what will happen, now you have to decrease the frequency, say 10 hertz is what I'm going to apply. So what it will do, it knows what is the modulus of the material at 25 hertz. So it will simply apply 0.7 times of that modulus. Okay, so it will take the modulus, it will consider the seed modulus as 0.7 times of the modulus. Then it will, based on that, it will find out the stress, and based on the stress value it will compute the strain. So if it is within the limit, okay, 75 to 125, 75 to 125, then it will keep the stress value as such. If not, it will vary the stress value, because from the stress and strain in the seeding cycle, it would have found out what's the actual modulus of the material at 10 hertz, and then this process keeps repeating. Okay, so this is how you will apply dynamic, you will apply loading to the bituminous mixture to find out the dynamic modulus. So now these are my 10 cycles of loading. Okay, and this is how my material will respond. Okay, my stress, this is going to be my strain response. Okay, there is going to be an irrecoverable strain. Okay, so this is my irrecoverable strain at any point in time, and this is my recoverable strain. This much is my recoverable strain. Okay, so even in the viscoelastic lectures, we saw that when a sinusoidal loading is applied, the complex modulus, okay, the absolute value of the complex modulus G star is sigma naught by epsilon naught, right? It is the ratio of the peaks, right? So here also you will just take the ratio of the peaks and say that it is the dynamic modulus. But in the case of, so here you will not take the entire value like this. Okay, you will remove the irrecoverable part. Okay, you will eliminate this part and take only this value as the amplitude of the strain waveform. Okay, so this is the recoverable strain, right? So the dynamic modulus will be the ratio of the peak to peak stress to the recoverable peak to peak strain. Okay, now moving on to the next question. Choose the incorrect statement with regard to dynamic modulus of a bituminous mixture. Okay. So let us go through the statements one by one. Dynamic modulus decreases with age. So what will happen with aging? You know that on aging, the viscosity of the bitumen increases. So if the viscosity of the bitumen increases, its stiffness is going to increase. Okay, which means its modulus of the bitumen, okay, as well as the bituminous mixture, okay, is going to increase. So this is an incorrect statement because it says that the dynamic modulus decreases with aging. No, right? Now moving on to the, let us go through the other options also. So dynamic modulus decreases with increase in temperature. So with increase in temperature, your viscosity decreases, and so stiffness decreases, and so modulus decreases. Okay, so this statement is correct. Dynamic modulus decreases with increase in loading time. So what does this increase in loading time mean? Increase in loading time or uh, decrease in frequency. Okay, so if the loading time is increased, which means the frequency is less, right? So in those cases, the material will be fluid like. Okay, and if the material is fluid like, then the modulus will be less. If the loading time is decreased, okay, so the frequency is increased. So if it is 10 hertz, what is the loading time? The loading time is 0.1 seconds. So if the frequency is increased, the loading time is decreased. Why is it 0.1 seconds? It is 1 by 10 seconds. Okay, and if if my frequency is 1 hertz, then my loading time is 1 second, which is 1 by 1. Okay, so in that case, if my loading time is less or the frequency is more, then the material response will be fluid like, in which case the modulus decreases. And if the frequency is high, or if the loading time is, if the frequency is high, or if the loading time is less, then the material response will be solid like, in which case the modulus will increase. Okay, then the fourth option is dynamic modulus increases with polymer modification. Yes, the dynamic modulus, polymer modified bitumen will enhance the properties of the bitumen. It will provide an increased stiffness, because of which the dynamic modulus of the bituminous mixture will also be more. Okay. In a dynamic modulus test, the maximum amount of variability is associated to water. So what is this maximum amount of variability? So when you apply a particular load to the sample, you have to check if, so you are applying a sinusoidal load. Okay, you say that it has to have a particular amplitude and it has to have a particular loading rate, right? Now you have to check if it is actually being applied on the sample, right? So to check that, you do this load standard error, and the maximum variability that can happen could be just 10%. In the same way, you find out the deformation standard error, deformation unity, and phase uniformity. Okay, deformation uniformity and phase uniformity. So when you do that, they have asked you the maximum amount of variability is associated to what? So it is associated from this table. You can see that it is associated to deformation uniformity. Okay. Moving on to the next question. How one can determine the zero shear viscosity of the binder? Okay. So a few slides back I was saying that I was explaining about Newtonian response and non-Newtonian response, right? Now, let us say I'm doing, I'm subjecting my bitumen to a shear rate sweep, which means I'm starting from the lowest shear rate that could be measured by my equipment to the highest shear rate, and then I'm performing a shear rate sweep. For a Newtonian response, my viscosity is going to be constant for all the shear rates. Okay. For a non-Newtonian response, okay, in most of the cases, my bitumen will exhibit a shear thinning response. Okay. In that case, how uh, the viscosity curve will vary is, it will have a constant viscosity at low shear rates, a shear thinning viscosity at intermediate shear rates, and a constant viscosity at high shear rates. Okay, so this is how my viscosity will look like. Now, to measure this curve, I have to perform some experiments on the bitumen, right? So in that case, I have to use an equipment. Now, any equipment which I use, okay, I can use rotational viscometer, I can use a dynamic shear rheometer. Okay, in if I say for example, let us say that I'm taking a rotational viscometer. Okay, it may not be able to capture all the three regimes. Why? Because it has torque limitations to it. So I cannot go below 10% or greater than 9% of the torque capacity of the equipment. If I do that, then my results, I cannot say that those results may not be correct. Okay, so maybe when I reach this stage itself, my torque limit would have reached and I would be able to measure only these two. Or in some cases, I can measure only this stage, which is when I do a shear rate sweep, I will be able to see only this regime. Or in some cases, I will be able to see only this regime. Okay, there it is very difficult to capture the three regimes experimentally. In that case, what I can do is, I can fit a model. Okay, so in that case, what I can do is, I can conduct a shear rate sweep. Okay, and if I'm able to capture this regime, then this viscosity will correspond to my zero shear viscosity. Either I can directly measure this value from the graph, or I can fit a model to it. Okay, and I can measure this and I can take this zero shear viscosity from the model. Okay, now there are two models. One is a power law model and the other is a cross model. If you see, a power law model can be used to predict only this shear thinning regime, whereas a cross model can capture both, can predict all the three regimes. Okay, shear thinning, zero shear, shear thinning, and infinite shear regime. Okay, so this is infinite shear and this is zero shear. Okay, so even if I have to use a model, I have to use a cross model, or I can directly do a shear rate sweep. If I'm able to capture this regime, then I can capture it. So it is not using a power law model, or I cannot extrapolate from a shear thinning model. If it is a if I'm able to capture only this regime, I do not know where this zero shear viscosity will occur. Will it occur here? Will it occur here? I do not know. So I cannot extrapolate from the shear thinning regime. Okay. So the answer to this is, I can either conduct a shear rate sweep experiment or I can use a cross model. Okay. Pick the correct option related to flow curve model. Power law model predicts all the three regimes of the bitumen flow curve. So flow curve is what we saw now. This is the flow curve. Okay, and as I said earlier, okay, a power law model can capture only this regime. So it cannot capture all the three regimes of the bitumen flow curve. A cross model predicts all the three regimes of the bitumen flow curve. Yes, because it has an equation which has parameters to capture zero shear, infinite shear, the slope of this, and the point at which it shifts from a constant value to a shear thinning regime. Okay. Bitumen exhibits only shear thinning behavior. So this is not. So this is correct. Okay, the second option is correct. Bitumen exhibits only shear thinning behavior is wrong because most of the literature say that it exhibits only shear thinning behavior. But there are a few literatures and there are few researchers which say that it exhibits a shear thickening regime also, a shear thickening behavior also. So that is one of my research works and it is still in progress. So yeah, so it will not only exhibit shear thinning behavior, it will also exhibit shear thickening behavior, and also it will also exhibit a Newtonian or constant viscosity depending on the temperature. If the temperature is very high, then it will not exhibit shear thinning behavior at all. Okay, it will exhibit only constant viscosity. Okay. And then the fourth option is the viscosity of the bitumen is shear rate independent. So no, because if it is showing a shear thickening behavior, okay, in some temperatures it will behave non-Newtonian, right? So if it is non-Newtonian, then it will be shear rate independent. Dependent. Which of the following statements are correct within the context of determining viscosity of mixing and compaction temperature? So I'm giving you a bitumen and I'm asking you to find out the mixing and compaction temperature, okay, of this bitumen. Now there are 4 methods to do it. So let us talk about the 4 methods and then we will come back. One is a zero shear viscosity method. One is a high shear viscosity method. The other is a steady shear flow method. And the fourth one is a phase angle method. Okay. So what do you do in each of these tests? Okay. So these two are determined using a rotational viscometer, which means it is a cuvette arrangement. What is a cuvette arrangement? It will have a cup and a bob spindle. Okay, so this is stationary and this is rotary. Okay, and these two are measured using a dynamic shear rheometer in a parallel plate system. Okay, your bitumen will be sandwiched between two plates where your top plate will either rotate or oscillate, and this is stationary. Okay. Now in the case of a zero shear viscosity, you do a shear rate sweep. Okay. When you do a shear rate sweep, you will be able to capture, so you may get something like this. Okay. Now here I do not know what. Now I have to do a shear rate sweep and I have to find out the viscosity at low shear rates. How can I do that? Instead of directly taking it from the graph, I can fit a model to it, say a cross model or a cross Williamson model, and then I will pick this viscosity. So this, let us say I'm doing it at 120 degrees Celsius. So I have to, finally all I have to do is I have to make a plot of viscosity versus temperature, right? So for a given temperature, I can use only one viscosity. And which viscosity will I use? I will use this zero shear viscosity. So at 120 degrees Celsius, I have performed this experiment and I have measured the zero shear viscosity. Then I will do the same at 135 and 165 degrees Celsius, measure the zero shear viscosities and make a plot, okay, in a log scale. And then I will pick the viscosity corresponding to, pick the temperature corresponding to 3 and 6 Pascal second, okay. So when I said that I have to find out the zero shear viscosity, I fit a cross model and I find out the viscosity corresponding to a shear rate of 0.001 second inverse, okay. So I will not simply take the zero shear viscosity, I will find out the viscosity corresponding to a shear rate of 0.001 second inverse, okay. Since the viscosity is very low, since the shear rate is very low, they are considering it as zero shear viscosity. Similarly, in the case of a high shear viscosity, okay, what you will do? You will again do a shear rate sweep, and here they mentioned the ranges also, 0.1 to 93 second inverse. You will do a shear rate sweep at temperatures of 135 and 165 degrees Celsius, two temperatures, and then you will fit an inverse power law model to it, okay. Power law model, inverse power law model, and you will pick the viscosity corresponding to a shear rate of 490 second inverse, okay. At high shear rates, you will pick the viscosity, okay, and that viscosity you will make a plot of viscosity versus temperature. For 135 you will be having one, 165 you will be having one. You make a plot and then you will find out the viscosity corresponding as a temperature corresponding to 0.17 and 0.28 Pascal second, okay. This is for high shear viscosity. In the case of steady shear flow or shear stress sweep, okay, you do it in a DSR. What you will do is you will do a stress sweep from 0.16 to 500 Pascal. So here you will keep on rotating the top plate, okay, and the top plate will keep on rotating in one direction such that the shear stress varies from 0.16 to 500 Pascal, okay. So it is a time domain test, it will go only in one direction. So if you see the plot of time versus stress, first I will apply 0.16 Pascal, then I will apply say 0.18, 0.20, like that I will go till 500. The rate of increase can be fixed by you, okay. Now what you will do is you will do this at temperatures of 76 to 94 degrees Celsius. Why are you doing it at such temperatures? Beyond these temperatures, your sample will flow out from the parallel plate system, right? So you will stick to these temperatures and then you will measure the viscosity corresponding to 500 Pascal, okay. You will apply the stress for all these values and pick the stress corresponding to 500 Pascal, okay. You cannot simply do it at 500 Pascal and take the value, because your material has a history your material response has a history dependent nature, right? So you have to subject the material to all these shear stresses before you apply the 500 Pascal and measure the viscosity corresponding to the 500 Pascal. Make a plot of again viscosity versus temperature, again find out the value temperature corresponding to 0.17 and 0.35 Pascal second. And the fourth method is a phase angle method. This also you will do it in a parallel plate system at temperatures of 50, 60, 70 and 80. Here phase angle means what? It has to have a frequency loading, an oscillatory loading has to be applied on the sample, right? So here you will do a frequency sweep, so which means your parallel plate, your top plate will not keep on rotating, but it will oscillate, okay, oscillate back and forth. So you will do a frequency sweep, which means I have to increase the frequency from, so I will do a frequency sweep from 0.001 to 100 radians per second, okay. And what should be the strain value? So it has, so since it is a sinusoidal loading, it has to have a frequency and has to have a strain amplitude, right? So we apply a 12% strain amplitude, and then now we get we will get 4 graphs, okay, for frequency versus phase angle at different temperatures, because at 4 different temperatures. Now we know what a time temperature superposition principle is for, right? So you plot a phase angle master curve, okay, reduce frequency, you plot a phase angle master curve, and then you measure the frequency corresponding to a phase angle of 86 degrees, okay. And that frequency, there are empirical formulas for mixing and compaction temperature. You use that frequency in the mixing and compaction temperature formulas to formulate to find out the mixing and compaction temperature. So these are the 4 methods, okay. So out of the 4 methods, let us see which option is correct. From the 4 methods that we saw, let us see which option is correct. Do we use a vacuum capillary viscometer to determine high shear viscosity? We actually use a vacuum capillary viscometer to find out the high shear viscosity at 60 degrees Celsius, but it is not used to find out the mixing and compaction temperature. It is used to find out, a vacuum capillary viscometer is used to find out the viscosity of bitumen at 60 degrees Celsius, right? And that viscosity corresponds to a high shear viscosity. Okay, so though this is correct, this is not used to find out the mixing and compaction temperature. This is just used to find out the response of bitumen at 60 degrees Celsius, or the viscosity of bitumen at 60 degrees Celsius. A cone and plate geometry is used to determine the shear thinning nature of the bitumen. Using a cone and plane measuring a cone and plate system, you can capture the shear thinning regime of the bitumen, but it is not used to find out the mixing and compaction temperature. A cuvette viscometer is used for determination of zero shear viscosity, high shear viscosity. A dynamic shear meter is used for steady shear fluid and phase angle method. So this is what we saw. This is the correct option. A Brookfield rotational viscometer is used for the determination of zero shear viscosity. This is also correct, but you have to see all the methods, right? So this comes under option 3, not the 4th, okay. So in the zero shear viscosity, the viscosity is calculated at a shear rate of what and at temperatures of what. So again we saw, we find out the viscosity corresponding to a shear rate of 0.001 second inverse after fitting the cross-Williamson model, and we do it at temperatures of we do it at temperature, and the mixing and compaction temperature is that corresponding to viscosity of 3 and 6 Pascal second, right? So we saw 3 and 6 Pascal second, not 3 and 6 Pascal second, and not for the other methods it is 0.23, 0.17 and 0.23, or 0.17 and 0.35. Okay, so moving on to the next question. The issue on using the equiviscous temperature to determine the mixing and compaction temperature for the modified bitumen is what? So here, if you use this criteria, finding out the viscosity, so finding out the temperature at which the viscosity is 0.17 and 0.23, okay, your bitumen, your modified bitumen is stiff, right? So at high temperatures also, its viscosity will be higher. In order to reach these viscosities, you need to go to even higher temperatures, which means your mixing and compaction temperature will be very high, okay, and unrealistic compared to unmodified bitumen. So in that case, so that is the disadvantage of using this equiviscous temperature to find out the temperature for modified binder, mixing and compaction temperature for modified binder, okay. So the answer to this is The temperature corresponding to Newtonian response is higher and unrealistic when compared to unmodified binder. In the high shear viscosity method, which among the following statement is true? Okay. We just saw what a high shear viscosity method is. So the viscosity is measured at temperatures of 165 and 185 degrees Celsius. No, it is measured at 135 and 165 degrees Celsius. Viscosity is calculated at a shear rate of 490 second inverse. Yes, right? You fit an inverse power law model to the curve and you find out the viscosity corresponding to a high shear rate of 490 second inverse. The viscosity is measured at 490 second inverse using a rotational viscometer. No, because you do the test only from uh, 0.1 to 93 second inverse, right? So 0.1 to 93 second inverse is the testing range in a rotational viscometer. So you do not measure it at 490, but you just calculate it at 490. The mixing temperature is calculated at a viscosity of 3 pascal second, and the compaction temperature is calculated at a viscosity of 6 pascal second. This is also not correct because you measure it at 0.17 pascal second and 0.28 pascal second. Okay. Moving on to the next question. Which among the following is incorrect with regard to a stress sweep method or a steady shear flow method? Okay. Viscosity is measured in the viscoelastic regime and extended to non-Newtonian regime. So if you see, you are doing this experiment only from 76 to 94 degrees Celsius, in which your material response will be viscoelastic. Okay. So yeah, so here but your mixing and compaction temperature will be, so here it has to be extended to the Newtonian regime, not non-Newtonian. Okay, so your mixing and compaction temperature is somewhere around 150 or 160 degrees Celsius, right? 150 or 135 degrees Celsius mixing and compaction. So in that case, you are doing it at 76 to 90, but you are extending it to the Newtonian regime. So this option is correct. Viscosity is measured from 76 to 94 degrees Celsius is correct. Viscosity is determined for a shear stress of 500 Pascal is also correct. A shear rate sweep experiment is conducted. No, you do a shear stress sweep experiment. Okay. In the phase angle method, the frequency is to estimate the mixing and compaction temperature is calculated at a phase angle of what? So just now we saw we calculate the mixing and compaction temperature for a frequency corresponding to 86 degrees. Okay, where it is starting to become Newtonian. Okay, not 90 degrees but 86 degrees. So moving on to the next question. Non-Newtonian behavior is characterized by what? So it is easy. We saw that a non-Newtonian behavior is something in which the viscosity depends on shear rate. Right? So it is shear rate dependent viscosity. It is not shear rate independent viscosity. It is not shear rate and temperature independent viscosity. It has nothing to do with temperature. Okay. So you should always talk in terms of shear rate and shear stress and shear rate independent viscosity. No. Okay. So the last question we already saw it last week. Okay. So here non-Newtonian behavior, I explained only these three cases, right? So this is a pseudoplastic case, this is a dilatant case, this is a Newtonian case. That is, this is shear thinning, shear thickening and Newtonian. There are other non-Newtonian, so I told that these two are non-Newtonian, right? So there are other non-Newtonian behavior also. One is it has to have an yield stress. If it has an yield stress, then it is non-Newtonian. And after having this yield stress, we saw all this in last week. What is this yield stress? Okay, actually the yield stress is the material will not, even if you apply till the material reaches a sufficient shear stress, gains a particular shear stress, it will not deform. Okay, so um, it needs some threshold value of shear stress. Okay, this is the threshold stress for the material to start deforming. Once it starts deforming, it can either have a constant viscosity or a shear thinning viscosity or shear thickening viscosity. Okay, and this behavior where it has a threshold stress and follows a Newtonian behavior is called as a Bingham plastic fluid. Okay, so these are the questions for this week. We will meet next week again with a new set of questions. Okay, so yeah.